And first, quick recap. We started by looking at theories in 2 dimensions which have conformal symmetry. And the way we started doing it was study the conformal algebra, which is the algebra of local conformal transformations on any 2-dimensional surface, possibly oriented but not necessarily. So the Virasoro algebra was generated by Ln with the following algebra. And even if we start with any Riemann surface, we can go to a patch and fix a point. We can go to a patch where the metric is flat, very ultra-local statement. And there we can study the transformations of that local complex coordinate, which rescales the metric by a position-dependent factor. On a sphere, some of these generators can be integrated to give global symmetries. And there is, in fact, a whole SL2C worth of symmetries on sphere, and then there is a U1 times U1 on the torus, and none on higher genus. Oh, you can't see? Maybe I can turn this. It's better, but I'll still start writing this side. Okay. On sigma g for g greater than or equal to 2. But what we are interested in is local physics to begin with, and for that, studying this algebra is sufficient on the sphere. And if we want to compute things like partition function and so on, then we have to sufficiently broaden our tools to compute things on surfaces of a higher genus. So, all right. Okay, so with that statement, let's focus on conformal field theory on S2. What we did was start from scratch by looking at the representations of this algebra. So suppose we pick a bunch of representations which I label as HI. Abhijit is here. Right. By the way, there are 2 copies of this in any physical conformal field theory, one for the holomorphic and one for the anti-holomorphic complex coordinate. And we are just going to concentrate on the holomorphic half and then see what kind of constraints conformal invariance imposes on that. And then the next step in the program would be to combine the holomorphic and anti-holomorphic halves to make a physical conformal field theory. I will not be able to talk about that today. So let's just focus on the holomorphic half. And then we start with a bunch of representations under this algebra, so-called highest weight representations, which have a state in that state space which satisfies this condition for n positive. So the remaining states here are all built up by Ln's for n negative, and they are all eigenvalues of L. They all have definite eigenvalue under L0, as we can see from this algebra. And there are subtle things that can happen where some of these states in the some of these descendant states might have 0 norm because of the central term and so on. And for a particular relation between C and these conformal weights, we discover these null vectors. So we have to remove the null vectors and the descendants that arise from there in order to make a consistent theory. Okay. So once we have these representations, I'm also going to denote the action of the L's on these representations by this pi I. This is just a technical definition to make writing things on the board simpler. Then what we would like to do is take tensor products. So if we were dealing with a finite group or a finite dimensional Lie algebra, we know how to take tensor products of representations. And here it's not so different, except that it has to be consistent with the fact that if we have 2 representations pi I and pi j of L which satisfy this algebra, then the L that acts on this tensor product should also satisfy the same algebra. In particular, should have the same central charge. And if we take the naive tensor product, as we can see, the central charge will add up. So we have to do something to make sure that C stays the same. And physics tells us the answer. It's just to consider the OPE of two. Okay, before that, I have to mention that there is a state operator correspondence here. So that is by starting by interpreting S2 as the complex plane with one point added at infinity, and considering the radial direction as time. So t equal to minus infinity corresponds to r equal to 0, and t equal to plus infinity corresponds to r equal to infinity. And we can start with the Hilbert space, that is direct sum of all these representations at the origin of the complex plane, and use L0 to propagate them out. So what happens in that case is that we can give a correspondence between states located at a point, that is this. So usually states are located at a constant time slice, which is a circle for radius not equal to 0. But because of a conformal invariance, we can always shrink that circle to the origin, and we can have a state supported at the origin. And a local operator is always supported at a point. So this tells us that there could be a correspondence between states and operators, local operators. And indeed, it turns out to be true. That given any state, or rather given any operator, if we take, we can even make the statement in the full conformal field theory, where we have an operator depending on z and z bar. We take z to 0, acting on the vacuum, we get a state associated with phi. And this is a one-to-one correspondence. So what we can do to figure out what a tensor product should look like, such that the central charge remains the same, is to consider the OPE of two operators corresponding to two states, one in each of these representations.
The operator to state correspondence is always there in any quantum field theory. Given an operator, you can surround it with a sphere and consider the state of it.
Okay.
But it's the other direction that is available when you have a quantum field theory, because once you have a state on a sphere, you have a scale transformation which allows you to shrink the sphere to a point.
Right. Okay.
I see.
So this is bidirectional.
One way always, but not the other.
And if you try to reverse it in an ordinary quantum field theory, if you just try to make the definition that I'll try to find the operator that would produce the same state. The point is that it won't be a unique definition, that there might be many operators that would produce the same state. Yeah. Of course, in conformal field theory, just Hamiltonian evolution.
Right. So we take an OPE of the field corresponding to L minus 2 acting on the vacuum, which is the stress tensor. Let me use the coordinate W. And two fields, or two local operators corresponding to two states in this. For simplicity, we can take them to be the highest weight states, the operators corresponding to highest weight states, which are the primary operators in the theory. So essentially what we are doing is, and let's take TW to be around a contour. Let's integrate TW over a contour around infinity and insert this Wn plus 1 to get the action of Lm. All right. So what we are essentially doing is take a sphere and put 3 punctures and put one of these operators at each puncture, and we have a 3-hole sphere, which I'll, well, maybe I should write it this way. I'll have TW here, and I have a contour around this circle, and I just push it across the sphere and make it into 2 contours, one around phi z1 and one around phi z2, and then see what happens. From this, what we get is the following. I'm not going to write this expression, but what we get is, for Ln, something like this plus a series with some coefficients of Ln times. So m. Which which also consists of this particular term ln times 1, which we would have had if we had taken an ordinary tensor product, but there is a further tail, which if we include and compute the algebra, we will get back the same central charge.
So here again you are taking the convention that Z1 is Z and Z2 is 0.
Yes, so by translation invariance, I can fix one of them to be at 0 and the other one to be at Z2 minus Z1, I guess.
And the CNs depend on Z.
And the CNs depend on Z, yes. It's a power series in Z. Okay, so this is still at the abstract level where I have an abstract generator and I input one abstract generator to get something that acts on a tensor product of the space. And
Naveen, you're remembering that you've stopped.
yeah, at 11:30, yes, yeah.
The review can
Go faster, yes. Yeah, I'm going to jump directly to the braiding parts. So I define this new fusion product to be the tensor product applied to the operation delta, which is also called the co-product. So what I do is take my abstract generator, split it into 2 copies in that description which I mentioned, and then take each of the copies there in that appropriate representation. And this is guaranteed to give us another representation in the same conformal field theory labeled by C. And now we can use this to construct certain vertex operators which carry information about the fusion of 2 representations. So what I do is take this tensor product here and project it onto and try to see what is the decomposition of this fusion product is in terms of these original representations. So I write so Nijk is the number of copies of pi k in this fusion product. And then what I do is if Nijk is non-zero, I can project a state here onto one of these particular representations pi k. And I get this particular operator which starts with taking a state in I, state in j, and giving a state in k, and it depends on the location z. And if Nijk is more than 1, then there is a particular value of Nijk corresponding to that particular copy of pi k inside this. So it takes a state in I, state in j to give a state in k. Now to convert this to an ordinary operator which acts on one state to give another state, I input a state here. So the pictorial notation is as follows. I have a state acting on j. I have an operator that acts on a state in j, controlled by a state in I. It could be any state in this representation, and it gives out that state in k. And it depends on the location of this object and also the channel in which it projects onto this. So this is what is called a chiral vertex operator. And in terms of this,
it's the part of the product of 2 operators.
Correct.
That behaves like a local operator situated
Yes.
at one of the 2 operators.
Yes.
In
In
a particular.
a particular representation, which is basically hk dual times hi times hj. So in terms of this 3 whole sphere, what we have is
So
alpha is a number. No, alpha is a number which runs over ijk. So now if I sandwich these guys, let's say between the primary states of hk and then take hi, z alpha. So this is j, k, and hj. So this, as we can see, is just something like z to the hj plus hk minus hi. Hi plus hj minus hk times a number. That is the fusion. That's the 3-point function of this holomorphic operator. So to construct a physical operator, we need to combine holomorphic chiral vertex operator with an anti-holomorphic chiral vertex operator with some linear combination coefficients, and then the final 3-point function would then be that appropriate linear combination of this times the anti-holomorphic part. Right. So in terms of this 3 whole sphere, I again have 3 insertions: one at z, one at 0, and one at infinity. I should put 0 here. So I have j here, I here, So these three can be at any 3 points, and I have used conformal invariance to put one at 0 and the other at infinity. Using the global conformal algebra itself, I can put these at any 3 points I want. And that's going to be important for the next step. So this basically encodes the representation theory in terms of the tensor product and so on. So now we would like to consider what happens if we take correlation functions of these vertex operators.
Sorry, this inner product in terms of operators, could I understand?
Which is the inner product?
So what does that mean in terms of a correlator? So do I have to take the operator, perform the inversion map, and then take the 2-point function?
Yes.
Is there a complex conjugation involved or not?
There is, there is a complex conjugation which retains Z to be Z, but then it acts on the space of operators. So it has the same conformal weight, but if we have other charges in the theory, that would get reversed.
The inner product between V1 and V2, is it, if I do the alpha, if I take linear combinations of the two vectors, do they transform with a complex conjugate of the linear combinations or not?
Yeah, it does. It does. So you're saying
So it's not just
I have V1, V2. Let's see. So the state V1 is defined to be that particular operator taken to infinity, but with this particular scaling.
But now suppose I take V1 to be, sum of 2, A times V1 plus V1 plus B times V2.
Okay.
If I just invert, it seems to me I get
A times
A times the inner product plus B times, not A star.
rather than A star. I think, let me for this to be positive definite.
There is the standard thing, right? The sum logic of inner product, it does not have this.
It does not have this conjugation. And there is,
if it's not important for you, let's go on.
there are two kinds of
Inner product.
inner product. One is the BPZ inner product, I think, which does not have the conjugation. The other one is the standard one, which has the conjugation. But all those are in the physical theory, where we have both holomorphic and anti-holomorphic parts. I have to think about what happens here, whether that constraint is required at the level of these operators, or there is, or whether that constraint is imposed after we combine the two halves. I'm sure there's an answer. I just have to think about it. Okay. So I would like to take correlation functions of this, and the simplest correlation function would be that of two vertex operators. But now we know that on one end there is a state in the representation HK. So if I have to combine two of these, I have to make sure that what comes out here should enter into the same representation on this other side. So I start with this kind of a description and put a P there. So there's a common state that propagates from this end to that end here. And I put these at two positions, and with the appropriate channels as well. So this is for theories where there can be more than one way of using two representations and projecting them onto the third. The Virasoro minimal models usually do not have more than one channel of projection. So this can be dropped in that case to understand most of the constraints that arise here. But this is the most general. Usually do have more than one. Yeah. Yeah, right. Correct. Okay. Let's see. So now I would like to. So first of all, this is. It would be the number of copies of that particular integrable representation that occurs in the tensor product of two integrable representations. Nij cases. There can be greater than one, if not zero. Okay. So some facts about this. So, first of all, the way we have written this here, we have put the origin here and infinity here, and this is well defined for radial ordering in which mod Z1 is greater than mod Z2. And we allow these vertex operators to have non-trivial monodromies around certain points. For example, when I take Z1 around Z2 and so on, and also when I take each of these vertex operators around the origin. So I allow branch cuts in the Z1, Z2 plane.
Now this mod Z1 greater than mod Z2 is tying yourself to a particular choice of origin, which was really
Sure.
arbitrary. So if you think of it from
Well,
the
if I have
quantitative
a-
point of view,
Right.
it doesn't seem like a very natural restriction.
Right. This is from an operator point of view. So I start with a particular radial ordering and then see what happens for different radial orderings.
But much of what you say could actually apply more generally.
More gently, yes. And it should, because I'm going to very soon, as we did last time, analytically continue to another region and then compare the two results to get some constraints on what kind of vertex operators we can have.
Yeah. But even these results literally would apply whenever the OP is valid.
Is valid.
And that has a much
Sure.
broader range of validity than
Sure.
one.
Yes. Yeah. Yeah. So I choose my branch cut such that Z1 minus Z2 is in the negative part of the real line, and similarly Z1 and 2 are also in that. So these are my branch cuts. So in the complex plane where these are put there is always a branch cut that extends from the origin to minus infinity along the real line. And at the locations of the two operators, there is a branch cut that goes this way and another one that goes this way to ensure that Z1 minus Z2 is in the negative part of the real line. So if Z1 and Z2 have the same imaginary coordinate, what this says is that Z1 cannot be behind Z2. And if it is and it crosses Z2 that way, then it will go to another sheet of the domain of definition.
You explained this at great length last time, but is notation Z1 minus, I understand.
So this is the branch cut.
Cuts like that,
Right.
as upstairs.
Mhm.
And then Z1 minus Z2 belongs to R minus. Is that where the branch cut is? What is that?
So when the imaginary parts cancel, that is when they are at the same height. So if I look at the Z1 plane, maybe I drawn it. Have I drawn it the opposite? Okay. So when Z2 in the Z2 plane, there is a chord. Okay. So it should be the opposite. Yeah. Correct. So it should be in the opposite direction.
So let me just try to understand. Now if you take Z1 minus Z2, the branch cut roughly is for R minus. That's what you're saying.
Yeah.
Okay, now I understand it.
Right.
All right. Good.
Right.
Excuse me.
So if let's see.
Last time you wrote does not belong to R minus.
Sorry.
What I remember last time you wrote Z1 should not belong to R minus.
That's the valid range of validity of the. So if I take one branch for this correlation function, that correlation function is valid when Z1 minus Z2 is not in R minus, which means the branch cut is along R minus in Z1 Z2 plane. So these are the branch cuts themselves which I've written. Is this right?
Here the diagram above is very clear that you choose, you make a choice
Yeah.
which you are choosing
Correct.
like this. Now the correlation function is very defined.
Right. I'm still not sure.
Actually, in principle, you should draw this thing
Mhm.
in one of the two. I mean, like the
In either the Z1 plane or the Z2
Z1
plane.
complex plane.
Right.
In which case there will be a branch cut at the origin, starting from the origin.
In the Z1
That's
plane.
Z1 equal to 0 singularity.
Right.
And the other one is Z1 equal to Z2 singularity.
Correct.
So there's only one branch cut above, and the other one is around R minus, right? Because either you are
Yes.
viewing it from the point of view of the Z1 complex plane
Yeah.
or the Z2 complex plane.
Correct.
In the Z2 complex plane, that branch cut will flip its direction.
Its direction because of
So
this
in the
minus
Z1
here.
complex plane,
Yeah.
it should go to the left, and
Correct.
in the Z2 complex plane,
It should be in the
so,
right.
You know, it's drawing it in the same
It's
diagram
not-
is a little confusing because it's not
Okay.
clear which complex plane you were drawing. Actually, there are two complex planes.
That's completely correct. Yes. I just drew this here so that we can see what happens when I flip Z1 to Z2 or the other way around.
Yeah.
So this is a simplification
So
of the
when it's
actual
another way
notation.
around, then it flips its tail because of the condition.
Sure, yeah.
Because Z21
Mhm.
would be then the positive real
Correct.
axis.
Yes,
Whereas
precisely.
Z12, which
Mhm.
shows up in the Z1 plane,
Yes,
it
would be in the
the
negative real line.
real
Correct.
axis.
Yeah, so
you're
this is
detecting-
a branch cut with respect to Z2.
Yeah, right.
This is a branch cut in the
So I
Z2
would
plane,
say that
and this is branch cut in the
yeah,
Z1 plane.
The two other way.
Is it the other way around?
Yeah. That
Sorry, this is a branch cut in the Z1 plane, starting at
it's a
Z1.
branch cut for the variable, analytic variable Z2.
Z2 in the Z1 plane.
I
And
mean, I don't understand why.
if I put Z1 at the origin,
Fix Z1.
yes.
Then
Okay.
the variable Z2 has a branch cut where you've drawn ending and Z.
Yes.
Right. So that's what I'm
Similar
saying.
Z2 plane.
So
Ah,
in the-
okay, okay, okay.
right. So
Yes.
in the Z2 plane.
Z2 plane with Z1 at the origin.
Yeah. And
So
by
I'm-
convention, that should be to the right.
To the right, yes. That is this. Right.
Because Z2 minus Z1 should be positive real.
Yeah, okay. Should be positive real for the,
In-
that's the location of the branch cut, yes. Yeah.
That is the-
We could just draw the diagrams and forget.
And then forget about this. Okay. So the point is when I try to extend this domain of definition of this, I have to avoid the branch cuts. And this is just a mnemonic. The actual calculation should be done carefully by either looking at the Z1 plane or the Z2 plane and then choosing the branch cuts appropriately.
But it's very clear because it's relative rotation.
Yes. So for relative rotations, this is good enough. All right. So what do I want to say next? Okay, so I have some expression for this in this domain of validity. And then I can analytically continue that to any other location.
One more question, since you're being so precise. When you draw many more guys, when you draw a third one, for instance, is that the branch cut with for the variable Z1 or for Z2? Say
It's
you
for
draw
Z2. It's for Z2. So let's say I draw Z3 here. I would put the branch cut this way
No,
because
I
that's
understand
for
what that
with
means.
respect to Z2.
That's with respect to the variable Z.
Z2, yes.
That means, sorry, now that you explained it, with respect to variable Z2, meaning you are plotting in the
If-
Z2 plane with fixed Z1, Z2, is that?
Z3.
Z1, Z3?
Yeah.
Okay, all right.
And I would like to take Z2 around Z3, then there is a branch cut in this direction.
But it seems odd to me that the second guy is special. It's like you're drawing one of the branch cuts to the right. Oh,
No,
which
it's
I think has to.
it's always the difference. So in this, so suppose I put one more here, which is Z3. In this ordering, I give the following branch cut structure. So in a different ordering, I will, if I just use these branch cut structures, then they will match up. Let's say I take Z3 to around half around Z2 so that they switch positions. Then Z3 and Z1 will have the same
Where is the
orientation.
eventual- when you do the OP of Z1 and Z2, is the final operator located at Z2 or Z1?
In this way of writing it, it's located at Z2.
Z2, okay.
Z2.
That's fine.
And then I do it with Z3, but then they'll have the same branch
located
cuts.
at Z.
And this appropriate branch cuts. And then I do that Z2, that resulting operator at Z2 with Z3. Well, I would like to reverse the direction. So I would do Z2 and Z3 first, and then do that with Z1.
I mean, wherever the final operator is being located, if it has a special direction for the branch cut, that makes sense.
That makes sense, yes.
Because that's the distinguisher.
Correct,
And then you'll keep putting it there.
correct.
Okay.
But the problem is when I try to braid them, for example, interchange the positions of Z2 and Z3 with these branch cuts,
It switches.
the direction switch, and then we have to relate that to the correlation function with the which branch cuts in this relative orientation. That gives rise to a linear combination. And then when we again flip, say Z1 with whatever is there at Z2 now, then again it will have an opposite orientation, and there will be a further change of basis to bring it back to this orientation of branch cuts. So that gives us one duality, a series of duality moves. And by duality, what I mean is that first I start with this, and I'm going to make the notation more natural this time. I'm going to also reverse the locations of the operators along with their labels. So last time I had retained Z1 and Z2 in the same order here, saying that there are two fixed points in the complex plane. That led to a lot of confusion. So what I want to do now is consider these two operators located at Z1 and Z2, and then do a transformation where this operator goes here and this operator goes here. So they reverse their locations. Now the branch cut structure looks like, can you see this?
Yeah, sorry, just to understand,
Uh-huh.
this operator goes here now means that originally mod Z1 was greater than mod Z2.
Yeah.
Now you want to consider the other.
Opposite, and actually take Z1 minus Z2 to Z2 minus Z1. So it's not just an arbitrary move into the other domain of definition. It's just a flip of the two coordinates. And now I'll get the following orientation of branch cuts. But then if I had analytically continued this expression with these branch cuts there, even for Z1 less than Z2, they would have had this orientation. So I have to relate this to that original analytically continued 4-point function. So then there is a matrix of basis change that happens. And that I would write as the braiding matrix B. So I have this I, J, K, L.
Okay, I would call this the analytically continued guy, and that the.
This guy?
Yeah.
So I start with an expression for this, and in that expression, avoiding the branch cuts, I've already analytically continued it to the.
So that's what I would call the guy that's analytically continued, the guy that when you move avoiding the branch cuts. And then you compare with what the expression would have been had you just chosen your definition with 2 and 1.
Okay.
Yeah.
Right. So you're saying solve for this conformal. This is called a conformal block, by the way. Solve for this conformal block when mod Z1 is greater than mod Z2. Separately solve for the conformal block when mod Z1 is less than mod Z2.
And then analytically continue this avoiding this.
Yeah, and when I do this, I have analytically continued the first one, but I already have an expression for the second one. Now I compare the two and I get this. Yeah, okay. That's more intuitive, thanks. So I have this. And there is, of course, the matrix of constants here, which I would write as so I have taken a sum over Q and over these channel indices, beta 1 and beta 2 here, to get something here. So I have written it this way, where I have related the original one to the flipped one rather than the other way around, because I would like this. So I consider these for given values of alpha 1 and alpha 2 as a basis for the space of conformal blocks, and the conformal block itself to be a linear combination of such guys over alpha 1 and alpha 2, and perhaps P. So I want the matrix B matrix to act in the usual way on that space of conformal blocks, which would be the coefficients of these guys here. So the basis vectors themselves act in the opposite way. So I am relating the coefficients of the flipped conformal blocks to the coefficients of the original conformal blocks using the same matrix. So the basis vectors transform in the opposite direction. So in terms of the sphere, now the sphere will have 4 punctures instead of 3. And let me label this in a cyclic way. When I write it this way, what is happening is I have cut the sphere in this direction and then stretched this to have a state along a state propagating in that direction. So I denote that by a cut like this. And this guy here is the cut which goes in the other direction. This might be a bit tricky to draw. So I maintain the order of operators. So this is a slightly complementary point of view on that. So now J and L combine first. So my cut has to go through so in such a way that it's kind of hard to draw. It's let's see. So I have to cut it such that something like this, I guess. So that I and K combine and J and L combine, and in that gap there is a state Q. So is this cut correctly? So let me draw it slightly better. Let me follow that stick diagram and then draw it. This might. Okay, so I have I, J, K, L. Now I have to combine J and L.
No,
So
the second one is IKJL.
No, I want to maintain the locations of this and cut it in a different way. Yeah, because I want to emphasize that it just has to do with cutting the 4-hole sphere into 2 3-hole spheres.
Actually, sorry, I didn't understand. I thought you were interchanging K and L. So how is that changing the way of cutting?
Sorry, K and J.
Oh, K and J.
Right. Yeah.
I see. Okay.
I'm interchanging K and
So
J.
you want J
And
and
L,
L together
yes.
first, and
Yeah.
I and K. And
So I want a 3-hole sphere which looks as follows. I have J, L, and then Q, and then Q or a Q dagger depending on which orientation we are looking at, and then K, and then an I. This one would just mean.
I think the diagram's clear. I'd really like to hear the identities.
Okay, okay, yeah. No, I just want to emphasize that this is in fact closer to what is happening in the physics side, which is I have a sphere with 4 insertions of vertex operators, and
I mean, you're saying convenient topology. I mean, there will not be any restriction to maintaining the position and taking J and L close to each other.
yeah, correct. And there is a cut which I can draw. I mean, because of conformal invariance, we can do the same thing by actually putting the states closer to each other instead of having an elongated tube here in between them. They're related by a conformal transformation. So it corresponds to, in the physics way of saying it, the 2 primary operators or 2 vertex operators which you are going to take an OPU of first should have their positions close to each other. So that is this particular configuration on this side, and it's this configuration here. So the whole thing boils down to putting together as many 3-hole spheres as required to make this n-hole sphere. And those are related by how in how many possible ways you can take 2 3-hole spheres to construct a 4-hole sphere. So there is this one, which is the braiding, and there is one more which corresponds to the next move, which I did not introduce last time. So in terms of the stick diagram, so when I draw a stick diagram, I've already gone to that corner of the space of 4 punctured spheres where K and L first fuse to give P. And on this side I have, another corner of that moduli space. Okay. So there is this fusion where I now take the locations of these 2 operators to be really close. So I fuse them first and then fuse the result with L to get I. So I have something like this. J, K, fuse first to give Q, and that fuses with L. So this one is at Z1 minus Z2. This one is at Z2. And again there is a sum. I need a bit of chalk. Of this matrix which I call as F. All right. So in order to define F correctly, we need to give normalizations for these 2 operator products as Z1 goes to Z2 in this case, and as Z2 goes to 0 in this case.
Okay, so this is definition of this F operation.
Yes.
Sorry, I need to understand. So what it was, this is like the associativity kind of thing.
Yes.
What is the relationship between that and the B?
This and the B?
Yes.
Well, right now they're 2 independent guys, and later we will discover a relationship between them.
What is the permutation of I and J mean?
Permutation of I and J. That would correspond to another kind of braiding, which is related to this by a series of F and B moves. So that is a constraint, for example, which we will discover.
But from the geometry of surface, it doesn't mean much.
It doesn't mean much. It is just, it is some kind of a braid, but with where I now put my infinity at say K or something, for example. So that relates the B matrix of this to the B matrix of that. And this is from these SL2C transformations on the sphere. So this is by, when I write this stick diagram, that's what I was saying. I choose this particular corner in moduli space where I have put L at 0, I at infinity, and I have put K close to L and J close to I. So there's a lot of choice that goes into writing the stick diagram. But these identities can be discovered in a much more natural way by just looking at 4 punctured spheres.
And in the second diagram, we've not, on both sides, all operators are at the same location.
Yes, I have not changed the location, so I have not gone to a different domain of definition.
If there's going to be a relationship between F and B, then B will have to be squared somehow.
Yeah.
So that the operators come back to that.
Come back to the position, yes, precisely. All right, so and also here there are two different definitions of B which I talked about last time, corresponding to okay, let me explain clearly. So this side of the equation is defined for Z1 minus Z2 not belonging to the R minus, where the branch cut was. Whereas here it was Z2 minus Z1 not belonging to R minus, which was the domain of definition. So these two are related, can be related to each other only in the common domain of definition, which let me see now. That would correspond to either Z1 minus Z2 having imaginary part positive or negative. So that corresponds to Z1 being above Z2 or below Z2.
Understand the last diagram.
Oh, this one?
Yeah, when she asked me the comment. So, first, your convention is L is at 0, K is close to L, I is
Here,
at
yes.
infinity, J
Yeah.
is close to infinity. let's say.
Correct. Okay.
And when you draw this diagram, just so I understand, L is again at 0.
Yeah.
And what do you mean? Why do you have to square it?
Sorry. Square it.
What was Shiraz? So I thought all the diagrams are being drawn so that Z1, Z2, their relative values are staying the same.
Yeah, this B business had the following flavor, right? You interchange operators 1 and 2, including the locations, and do it in two different ways. One is analytic continuation, second using the definition, and what's the relationship. Whereas this F thing is just
interchange the operators including the location, but then bring the locations back.
then you compare the relationship between these two things, right, with the interchange. On the other hand, this F thing has all operators. You're comparing two things with the operators in the same place. So if you're going to relate that B to the F, at least
Which operators are K,
So
J,
all
and
operators are fixed at the same place, but I
On
do
the
the
two sides
OPE
of
of
the equation.
on the two
You
sides,
mean there's same place meaning is Z1, Z2?
Z1 and Z2.
Yeah.
But I do the OPE of J and K first on the right hand side.
Yes.
So that is this.
Is it? I see.
So it's a rough intuitive statement. The intuitive statement is that so you've got some operation here where what you're doing is taking an operator Z1 and Z2, interchanging them in two different ways in the first thing,
Yes.
and comparing them. But and the second thing is a more traditional kind of conformal bootstrap thing, where you're not changing the positions of the operators.
Correct.
So there's a way of getting back to the second thing by taking these two things and taking them around again.
Oh, you're trying to relate F and B,
B,
now,
F and
right?
B.
Which second?
The
No,
second-
he's trying to.
F is a F.
Right. If there is a relation between F and B, there has to be more than one B and an even number of Bs,
Yeah.
because B relates something where
It's a half integer.
It's
Yeah,
a little bit
Z1
what we call I pi.
it's e to the I pi. It's precisely e to the I pi when Z12 goes to minus Z12. Whereas here Z1 and Z2 the relative orientation is not changed. So in order to compare, if there is a relation between F and B, then it has to be such that the number of flips is even.
Of course, as you said, F and B are just matrices. So, I mean, there might be a relation anyway, but just intuitively it feels like B squared should be possible.
Right. So here, as we can
And
see,
Fs are what you call 6J symbols, right?
yeah, these are the 6J symbols, yes. The generalizations of the 6J symbols, I guess. So I have B here, thanks. So if we can look at this diagram, what I'm doing here is, this is in a corner of the moduli space where Z1 is very close to Z2. So Z1 minus Z2 is very close to 0. So I'm doing Z1, Z2 first, and then doing the OPE with something at 0, because that's the order in now. But I have not changed the order of Z1 with respect to Z2. One could also do this and then follow it with this, or the other way around. And then we have to discover consistency conditions with that, okay? So these are the two definitions here. There is also,
So this is the thing that in the ordinary conformal.
this is the, this identity.
These 6J symbols, it's not so clear that they're well defined for physical representations in, let's say, higher than 2 dimensions, right? This is the thing that's complicated in
Oh, in theories, conformal theories in higher dimensions?
3 dimensions, for
Right.
instance. There's this principal series for which this seems to make sense. It's not clear that it's well defined, or it's
I
not
see.
well understood.
In higher dimensions, anyway, you don't have just the chiral halves.
We don't have that.
We don't have this
Let's say
interpretation
we have the whole, the analog of this for the whole.
for the full physical
The
theory.
full thing, see, what exactly is the statement that you can do the OPE in
It's the same diagrams, except that these are at.
Algebra, the representations. One copy of Virasoro. What with the representations of Virasoro times Virasoro. That would be this. You could write a similar statement probably.
We could have a similar diagram where these are not interpreted literally in terms of 4-hole spheres and so on, but just as a mnemonic for correlators. You can use the same diagram with Z1 and Z2 being two locations in R4 or something, for example.
Yeah, there's no analog of the top line for the full thing. Because
There is no braiding, because that can always
the
be.
bottom line is not a monotony.
But that should exist.
This exists
Yeah,
in higher dimensions
Yeah, the top stuff is all because you're holomorphic stuff.
and in 2 dimensions, because
And-
we cannot undo it
And
with
okay, I see that was the
a
point.
basis change.
Okay,
Right.
thank you.
Right. I mean, we could have avoided the branch cuts if we were in higher dimensions, for example.
So only this last line
Will survive.
Bootstraps.
And that's also for the full correlator. There is no, well, at least in the usual sense of conformal field theory in higher dimensions, there is no way in which we can do holomorphic times anti-holomorphic.
And in high dimensions, it's not so clear that defined in exactly this way for the actually unitary representations, that thing is so well defined. If that F, Abhijit knows all about this, but I mean, it's not such a different
Yeah, this part I don't understand, because I thought that the second equation is more closer to the regular conformal bootstrap equation.
Yeah, but now we're talking about conformal blocks in
So
the
the usual conformal bootstrap equation is slightly different, right? It's this. So here you are expressing one conformal block.
Yeah.
In terms of the conform block in the other channel. But the usual bootstrap statement doesn't quite do that. It is. I mean, it relates sums on both sides. In order
So I
to
sum
go
over
to
P
this-
here.
Yeah. In order
Right.
to go to this equation, you would have to find some sort of an inverse
But you
on
have
one
this,
side.
but you
So
have this
that
cross
one
ratio,
term-
you have this cross ratio variable, U and V, and then when you take a power series expansion of the usual conformal bootstrap equation, doesn't that single out one conformal block on one side and the sum of conformal blocks on the other side?
So the equation still corresponds to the sum on both sides.
Yeah, it is sum and sum, of course, to begin with, but then there are these the functional dependence on the cross ratios, and by manipulating them, I thought,
You can reduce it to one thing.
You would imagine, right? But it's not that. It's not that clear.
I see.
It may be true, but it's not that.
I see. Okay, good. I got the point now. Yes.
Yeah, so there we start with just.
Something that is group theoretically nice. So the group theory, if you the representation theory of the conformal group in higher dimensions, from that point of view, these principal series representations are nicer to work with. And if you work with those representations, then you would find such an object.
I see.
I mean, the question is, are these unitary conformal blocks a basis of some well-defined set function? What well-defined? You know, that whole issue itself.
Yeah.
Oh, it's kind of issue trying to get to.
Yeah. Okay. I got it. Yes.
It's like quasi-nominal. It's very much like quasi.
I see. Okay, so now for some constraints. So there is also something which we need to define for the torus with one puncture, which I'm going to skip. And let's just study the identities in genus 0.
That's
And then just say that genus 1, there are further identities that come up. But just for completion, we can take this.
Just one comment. I mean, the way a function on a real line has a good basis, you need the IPX and not need the PX. That's why you need to have this imaginary conformal dimensions for having a good basis.
I see. Okay, to just get the conformal block on the torus with one puncture, what we do is take this this chiral vertex operator, identify these representations, and then trace over that, and take a state here. So pictorially, it would just mean doing this. And the trace would be with a weight called Q, L0 minus C over 24. So the Q tells us how to identify this as we go around the torus. And this corresponds to a puncture. So this would correspond to in the diagram, this where I have this state V in representation I. And then I study how this changes under modular transformations of the torus and so on. So that gives rise to, first of all, one additional matrix of this kind corresponding to the S transformation, where tau goes to -1 over tau. And so I have 3 matrices. And there are various constraints between them by studying 5-point functions here, as we will see now, and 2-point functions on the torus, which I'm not going to talk about.
Here you're just talking about how 1 point, and you said this, but
So this is
functions change under modular transform.
under s tau going to minus 1 over tau, where q is e to the 2 pi I tau.
So just like the partition function blocks themselves change under modular transform, so do these 1 point functions.
Correct. So partition function would just corresponds to taking this to be the vacuum.
Right.
And sorry, I should know this, but if you take a 1-point function of some primary, mixes with the others, or what happens? I mean,
You think of it in Hamiltonian language, either tracing this way,
yeah,
or tracing
that's
that.
what I was
The full theory, of course, is the same.
Yeah.
In the blocks, it's not.
That corresponds to this.
Yeah.
Right.
some combination.
Correct. It corresponds to cutting this either this way or this way here. So that gives rise to another matrix, which is the S matrix.
Okay.
Okay.
So then you were saying you have S,
B and F. Two B's actually, depending on whether imaginary part of Z12 is positive or negative.
Okay, yeah, there
One is the inverse of the other.
Okay.
Yeah.
All right, so up to that inverse, you have 2 matrices and S.
And S, yes.
And now you're going to think about constraints.
Constraining them.
Wait, and the number of such blocks, sorry, but the number of these torus blocks,
Right.
is that the number of primaries square?
For 1-point blocks, yes. Yes.
Is the number of vacuum blocks or just number of primaries?
Yes. So here I have one extra freedom of inserting
Which one?
primary there. Yeah. For 2 points, it just proliferates appropriately. Okay. So let's study the identities.
There also you could have this label, right, alpha.
Certainly. I didn't put it there, I guess. Yeah. For Virasoro minimal models, they are not present, but we're usually interested in more general things where we can also have that fusion.
What is the index?
Which index? Did I just erase it?
No.
Okay.
The alpha in the 1-point function.
In the number of ways you could make a singlet out of P and P.
So it's just the same alpha which is here, but then giving back this j,
Giving, I see.
and then I do the trace.
But then you're tracing and you're also summing over J, right?
I'm summing over j, yes.
So then the alpha may change depending on the J.
Certainly, yes. So I have the space V, I, j, I is at z, and j is at 0 to begin with, giving k. So now I also identify that, and then sum over j. And alpha is just an index for the basis of V, I, j, j. So alpha itself can change with j. So this is a big direct sum of vector spaces.
So ultimately, after summing over the J's and the alphas, you will get something as a function of I.
Yeah. That would be the one. Yeah,
So the
1-point conformal block.
Is limited by I and J.
I and j and alpha.
And of course, no, the alpha is in transformation.
Okay, so usually
Block
what?
itself is limited by I and J.
Oh, that was your point. I see.
No, but j is also usually summed over in the sense that I take the different S matrices corresponding to different j and put them as a big S matrix.
Wait, but I can
Then
think of
it's-
a block with a J and an I.
And then I, yes, yeah.
Okay.
And then it takes V, I, j, j to V, I.
I was thinking of the thing summed over.
The S. The S will now mix the alpha index and beta index if we don't have sum of.
So the S we can
That's-
think of also sector by sector for each J and R.
Yeah.
Yeah.
Okay, thank you.
And there is an I dependence also, of course.
Sorry,
Which is fixed.
when you do the modular transformation, then the J would also mean on the right, on the,
Yeah, so the modular transformation is well defined for
you're going to get some more.
the sum over j, V, I, j, j to what k.
No, you want to
Then
keep
this would
only
be-
one element somewhere. You just want to understand how it acts on one block. Why is
I'm trying to see if when I do a modular transformation, okay, I already have a 1-point conformal block which is indexed by a state from I, state from I, and this alpha, and I've summed over all states in J. So one would like to study how that changes under tau going to -1/tau. That's the question you're asking.
J is not summed over. You want to see.
No, J is not summed over. States in J are summed over. That's the trace. And we would like to study that single one summed over. Yeah. And now what you're asking is, how does that change under tau going to -1/tau? Just that 1 point conformal block. Right. There is a matrix which is S I J. I should use a different S I K, I guess, given by J. Let me get rid of this. Alpha and beta, starting from V, let's see, I J J to V I. But alpha is an index here and beta is an index here.
But just suppose I just think of I and J as composite.
Well,
then you've got a matrix in this composite.
wait, have I mixed it up? Just a second. I think this should be K. So J is still traced over, but the primary that I inserted the puncture can change, and that's the mixing part here.
So
And it also cycles.
you've got a block labeled by insertion and which guy runs. Let's call
Correct.
that I and J.
Right.
Now, I and J is a linear combination of I prime and J prime, running over all I prime and all J prime.
Even J prime,
Why not? If I if
when I do
suppose
tau
is
going to
I-
-1/tau.
I is fixed on both.
Why is I fixed?
It's like an external guy. In the F definition also, the external guys are fixed.
But when you take
So
the
this
linear
is
combination,
this is an I.
I see. You say that just because of the weight
Yeah.
of the block. Right.
So you're saying I is fixed when I do
think
modular
the cleanest
transformation.
If you write down the equation that you had for F and B for this guy.
Okay. So I have an I and I have the point of intersection and I have alpha and J running through the loop with a Q also, right? Under tau going to -1/tau, what this would go to, okay, is a sum over some beta and some K of, I, K going here, and this is Q prime, this is beta, and Z, Z prime actually.
So I doesn't change in that process, but the intermediate running block changes.
Let's
So
see.
the S matrix in a sense
Right.
is labeled by some fixed I and then is a matrix in J and K and alpha.
Right. So I have a matrix I and something with a JK and alpha beta.
Okay, now I'm with you.
That's the matrix that goes here
What we call as matrix usually is when I is vacuum.
when I is vacuum. Yeah. But we also need to consider these other ones to constrain the possible representations that one has.
J is the state, J are the states running the loop. So
Yeah.
what is Q?
Q is that particular parameter that I use to stitch these two ends together.
Oh, just
So
use
it's
the,
that e to the 2 pi I tau. Yeah.
There is no Z and Z prime.
Sorry? Z also transforms. So Z is identified with QZ in this. So Z prime has to be identified with
No,
Q
what
prime
I'm
Z.
saying is that the way you used conformal transformations to fix something, right?
Correct.
On torus you can do that to fix Z.
Ah,
So,
I see.
In other words, there is only one modulus for torus with puncture, which is tau.
Is that right?
Z and Z prime.
Is that right? So you're saying I can fix the location on the torus by global conformal transformation, which is one of the rotations around the circle. I see. Okay. So, all right. I've always seen this written in terms of Z and Z prime. Maybe because they would like to extend it next to 2 point and 3 point, I guess. And then use this particular decomposition in which it reduces to two 1 point blocks in the torus and so on. Okay, so let's study identities on B and F now and keep S aside. There is this particular one which has the following. So we saw the Young-Baxter identity last time, and I'm not going to do that. Let's look at this one. So I take a 5-point function. So I'm going to leave these ends unlabeled because those are not going to change in the moves. So when I write B12, for example, it means I perform the braiding for the first two on the top. And similarly for F. So I would like to look at this.
This diagram, where is it? When you do the OP, which order are you doing it in?
So again, I fix this to be at 0 and this at infinity. So I just do the OP like this.
Like that.
So I do
JK OP and put the final result.
No. K with this first, and then this with J, this with I, and then this with I. Yeah.
And fix it all at the location of that last guy.
Last guy, yes. Yeah. To get a state there.
I never think of states.
Okay. Okay. All right. So the identity which we are going to look at is
yeah, it's operator.
Correlation function.
Yeah, correlation. It's a function on this. And you're doing OPs. There's no particular for this diagram. Forget about it. You've got OPs.
okay. So we have to show that the two sides of this equation are the same one when it's applied to the diagram. So let's look at the left-hand side. So I do F12 first. So that's fusing I and J. That is doing the OPE of Ij. So I'm going to a different corner of the moduli space where the locations of these two are really close to each other.
And then you put the final answer at the location of J.
At the location of J, yes.
Okay.
And
Yeah.
your nomenclature is you're numbering 1, 2, 3 from the left.
From the left, yes. Okay. So I always adopt a cyclic ordering which goes clockwise. Clockwise. Yeah. So I have this now. And then I do B13. So when I say B13, I should label the points where these things are happening. So these are really close to each other. So in fact, let's see. So this should be kind of on the top of everything because this difference is really close to 0. But I'm trying to see how to interpret this. Let me just do B13. So I have to interchange the first and the third locations here on the sphere. So with some orientation, and that orientation is fixed here. So that would mean something like K, Ij. And then now I do the right-hand side on that. So I have a B23, the same orientation. So that would be I, K, J, and B13. B12, sorry. So that would be K, I, J, and then F23, which gives this because I fuse I and J together. So there is this loop here, which means that this has to be satisfied in any theory where I can define these B and F matrices.
Let me make sure I understand that. First you fuse 1 and 2.
Yeah.
Then you want to take the OP of the product of that with the last guy.
Correct.
So you have to do some interchange.
Yes.
For it.
Yeah. Oh, you mean there itself?
There, on
Yeah,
the
on the
left
left
hand
hand
side. Here,
side.
what
Right.
did you do again, please?
I did B13.
Which was, can you, which is 1 and 3 here?
This is 1, 2, 3. Here. This is 1, 2, 3.
Okay, so you interchanged 1 and 3.
I have interchanged 1 and 3 in this, which is put
Yes.
K this.
And then what did you do? What fusing did you do?
The fusing has already been done. This was fusing first, which I have fused 1 and 2. And then I have this ordering. Now I have interchanged 1 and 3 by this.
Right, so this way and this way are the two loops.
Yes.
Okay, so first you fused
1 and 2. That gives this.
Okay. Then you.
But I fuse it in such a way, such that the resulting operator fuses with the resulting operator of this fusing. That's with this.
Okay. Okay.
Okay. So I go to this domain where this point of insertion is still the closest to 0. But these two insertions are closer than Z2 is to Z3. So that is that domain.
Yeah, so there are operators here and here.
Right.
There are 5 operators totally.
Yes, yes. So those are always fixed.
Okay.
Then now I do a B13,
Uh-huh.
which is flip the locations of this operator here and this operator here, which arises as a fusion of this.
Yes.
So that is this.
Yes.
So now I stop there
Okay.
and apply the other one, other sequence of moves.
Okay.
So I start with B23, that is flip these two.
Yes.
That's, let me label 1, 3, 2 now.
Yes.
And then I do a B12, so that becomes 3, 1, 2.
Uh-huh.
And then I fuse the last two.
I see.
So each of these corresponds to the locations in that particular
I see.
diagram,
I see.
that stage, and not the original labelings.
So, Naveen, so
Yeah.
in your Young Baxter, it was like BBB was equal to BBB.
BBB,
right?
yeah.
So there are odd number of B's on the left and odd number of B's on the right.
Correct.
Now you have an even number of B's on the right and
Right.
an odd number of B on the left.
Right.
So if I'm thinking of each
So
B
there
as
is-
some kind
okay.
of a half rotation,
Okay.
then I'm a bit confused.
Yeah. So now, good. I was about to say that about that. We usually include an operator called P23 here, which is the permutation. So that corresponds to permuting the second and third vector spaces. It's not a physical interchange of the locations like B or F, or a change in locations like B or F, but it just flips the vector spaces
So the
back.
analytic continuation.
The analytic continuation, wait, is that true?
If you've just applied an odd number of B's, you've also, I mean, you.
No, I've always brought it back to the same solution before comparing, but the vector
isn't
spaces
that
are flipped.
ultimately what bringing it back to the same solution?
So when I apply these things, what happens is if I look at it as the action on the vector spaces, let's check that. I have hi times hj times hk, which I'm going to write it like this. I do f12, then I get, how do I represent this? Okay, let me be more careful. How much time do I have? Are there anything? Okay, let's just focus on this and try to get this right. So I have the spaces, which let me label these as PQ.
I said it wrong. On the right hand side, you did B12 and B23.
Yeah,
So you switch the positions of 1 and 2,
right,
and you switch the positions of 2 and 3.
correct. That is this.
So effectively, it's like switching the positions of 1 and 3.
That's okay, but there is still this permutation operator that's required, which switches the positions of 2 and 3 here. And we can see that by actually looking at the action on the vector spaces.
What does the permutation operator do? Is it, I mean, so that fusion means that you take I and J and you fuse them.
Correct.
You think of the resulting operator, I thought, at the location of J.
Yes.
When you permute it, are you saying actually you should fuse them but think of the resulting operator at the location of I?
Yeah, you can think of it that way, yes. Yeah. So I and J are at, initially they were at different locations. Now they're at Z1 and Z2, let's say, for example. Then you fuse them and the resulting is at Z1 minus Z2.
Okay. Yes.
Or if we put Z2 at 0, then it's at the location of Z1.
Yes.
So we just fuse them in the opposite order. But they'll still, so that would be something like put J at Z2 and I at Z1 and fuse them so that and then put it at Z1 back.
So there can be some phase there also. That is what you're wanting to account for. Is by this.
No, there is no phase there because I think what Shiraz said is right. It is just the analytic continuation of the original block without doing this flip.
Your analytic continuation will pick up a phase. What I'm saying is, are you doing the following? Suppose you were getting
Okay.
Z1 minus Z2 to some power.
Okay.
Then when you do the permutation, you regard it as Z2 minus Z1 to the same power.
No,
So when you, no, that's
no,
not.
Z1 minus Z2 remains the same. I don't want to do any more physical interchanges of the operators. If I consider these B's to be acting on these space of couplings, for example, in that first case, what is happening is, let me label this as AB. Then this F12 is acting on, let's see, it acts on the space where I fuse Q and J first to give P. And then I take the resulting P and fuse it with I to give A. And then I sum over P. So F12 acts on this to give an element in B, this here, where I take this to be some R, for example. Then there is a fusion of J and I to give R, to give S, and I fuse, well, this is the same as Q, and I fuse S and Q to give A. So when I repeat this kind of an action and see how the vector spaces act, what happens is at the end, what I should get from here and what I get from here, they have the locations of I and J interchanged in this.
I can't see that graphically.
Okay, so it's something like, graphically I should have, if I wanted to show that explicitly, what I should have done is retained the position of J to be between I and K. So that means I should have put it as this. Right? Because I'm interchanging 1 and 3 without changing the location of 2. That's what you wanted to say. Okay, yeah. And then I flip the direction, which is taken care of by 3 to 3. One can also draw the diagram which I did last time about these, having these strings starting from this, which start with 3 and then do F12 first. So I'm fusing, which just means I get this kind of a thing where the 2 strings fuse. So the earlier picture where I had 6 B matrices, there was no fusing allowed. They could just cross either beneath or below or above each other. Now this F fuses the string, and now after that, what happens? Let's see, 1 and 3.
Hey, the QCD people have already.
Oh, they have. Okay, I
already
have
asked me when we leave.
2 minutes. Okay, I can skip this then and leave it as an exercise.
But okay, either way, it's some analytic calculation that you have to do, I think, right? Ultimately in 2 and 3.
Yeah.
What else can it be? That you some function of the coordinates.
Yeah.
Okay.
I think we just kept Z1, Z2, Z3, Z4, Z5 in these diagrams and see.
Okay. Even the locations of the
locations
middle
of
3
all the
guys,
points.
maybe not even the first and last, right?
But
Okay.
we've got 2 minutes to reply.
Okay. So there are a bunch of these identities, one of which is this, for 2 signs of epsilon. The F matrices do not depend on epsilon because we are not really changing the order of Z1 and Z2. So what happens is I can solve this equation for each epsilon, plus or minus.
I forgot what epsilon was.
It was that sign depending on whether imaginary part of Z12 was positive or negative. And one matrix was the inverse of the other. So B epsilon was B minus epsilon inverse.
Yeah.
So it was taking Z1 and Z2 in the clockwise direction or the counterclockwise direction depending on their locations. So we can solve this equation for 2 epsilons, and then there is the Young-Baxter identity, or there is an the Young-Baxter identity, or you can replace the Young-Baxter identity by combining that with this to get other equations only on F. So the idea is, eventually what we discover is the information contained in B is also contained partially in F, along with some simple relations for B, where I have, instead of these 4-point blocks with 4 general insertions, I take one of them to be the vacuum representation. Either this or this to be the vacuum representation. Then B becomes smaller, easier to write down, and it's those matrices, one corresponding to this arrangement, other corresponding to the matrix, the vacuum representation on this side, and the F matrix, which are sufficient to describe everything at genus 0. And then I have the matrix S at genus 1. And then I have these various identities for at genus 0, which has, this is called the pentagon identity, and there are 2 of those. And then there is a hexagon and so on.
So just 2 minutes before we end, so what good are these identities? Can you solve for them, for instance, in simple situations?
In simple situations, one can solve for them, like for example the Ising model, where the Nijk's are quite small and either 0 or 1.
You have to put in what the Nijk's are?
Yes. So like I said last time, the spirit of this program is to choose all possible values of n's and then see whether these identities give consistent.
Go and have chat.